crystalline form. I'll show you here the experiment. This shows the formation of non-crystalline alloys of components that are immiscible, and the system which I'm showing here is iron and copper. Iron and copper you can mix in the molten state, but you cannot mix it in the crystalline state. So in order to get this nanoglass alloy, we started with a two-phase nanoglass. The black ones is a scandium iron glassy cluster, and the white one is a copper scandium nanoglass cluster. And then we bring them together, so we get a nanoglass, and here is the lateral distribution of the copper and the iron atom, and you see yellow is the copper, and you see from the fluctuation in brightness, bright means a lot of copper, and dark means less copper. We have the fluctuation which you expect, of course, when you bring the clusters together. You get areas where there's more copper and areas where there's less copper. Same is true for iron. Bright, there's high iron concentration, dark, low. And then we're nearly at 100 centigrade for 3 hours, and what we get is a very uniform distribution. So what we have formed is an amorphous copper, iron, scandium amorphous structure, a solid solution, a structure like this. And then we try it the other way around. We mix copper and iron in the liquid state, which is no problem. When you solidify it, the answer is this. You get iron precipitates in a copper matrix. That means even there it's mixed, in the end you get this, and in the glassy form you get that. This is the sugar in the coffee, and this is the sugar in the ice. So you can then form alloys of compositions which did not exist so far by means of these nanoglasses. And that, of course, should open up a wide spectrum of materials where we bring elements together which we couldn't bring together. So this is just a first test of the idea. We have no idea what the properties of these things are and what the future will look like. I just want to indicate that by just this simple idea to go away from a melt-quenched structure to a composite structure, a whole new world opens up. And now I want to turn away from the things. I'll show you a new effect, and this is to talk about nanoglasses that deviate from charge neutrality. So far I was talking always about systems which are charge neutral. Now, of course, there's no reason to be charge neutral. We can also push the nanoglass into a charged state. And that will lead us to the so-called tunable, electronically tunable materials. The way we produce these things is very simple. We take a two-phase nanomaterial, either crystalline or glassy, a black and the white, and then we etch away, remove one by etching one. For example, the black part is removed, and then we get a material which is called a nanoporous material. So we are left over with the clusters, with the white clusters and holes here. And then we fill into the hole aqueous electrolyte, and then we apply a voltage between the electrolyte and this nanoporous crystalline or glassy material. If we apply an electric voltage between the two, then we get, of course, an interface, a Helmholtz interface layer. And in this Helmholtz interface layer, we can create very high fields, about 10 to the 8, 10 to the 9 volts per meter. And that means that the surface atoms of these nanoporous materials are charged by half an electron per atom. And now, as 50% are interface atoms, that means about 1/4 of the valence electrons are pulled out of the material. So you shift your element about 1/4 to the left or to the right in the periodic table. And that, of course, should then change the properties dramatically, the magnetic properties, electric properties, density, and so on. And I'll show you in a minute how much that can change the things. So this is a way how we produce them. Essentially, a nanostructured material, etch one component away, fill an electrolyte in, apply a voltage, and then already you get these results. An example is